Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to lecture number 7 for the course series of electronics. My name is Engineer Jaffar Ali and I am instructor for this course. So let's start with the recapitulation of the previous lecture. In the lecture number 6 of this course, we have discussed about the working of the transistor as a switch. We learned about the things that are involved while you are using the transistor as a switch. We also discussed about a curve that provides you the working conditions for the switch. The first one is basically the cutoff region where the switch is normally off or the circuit is normally open. So the circuit is open, the switch is termed to be off. Then there was the another region, this is known as the linear region, where you increase the current and the voltage, the voltage and the current increases, the output current increases basically. So this was your, uh, this region was your linear region, or you can say active region, where you can amplify basically to the transistor, the output of a transistor. So in this area, the transistor will be termed as the amplifier. So you can amplify this region. While increasing x-axis, you can increase the y-axis as well, or the amplitude. The last region, which was basically this region, was known as saturation region. Saturation region, and this region was termed as normally close. Normally close. It means the circuit is on. Switch on circuit. The switch is on basically. So if the circuit is normally closed, the switch is termed to be on. If the circuit is normally open, the switch is termed to be off. This is basically the cutoff region, and this is basically the saturation region. So in saturation region, transistor acts as a closed switch. It means the circuit is on, and in the cutoff region, the transistor acts as a open switch. It means the circuit is switched off. So this was the transistor as a switch, and we also discussed one numerical in the previous class. So in today's class, we will be looking at some other numericals regarding this transistor as a switch. And after this class, you will be able, you will be in such a position that you will be able to understand this working of the transistor as a switch with more accurately. So let's get started. The first numerical is basically about the transistor as a switch, and the transistor is basically the NPN transistor. This is mentioned that this is NPN transistor, and it is as working as a switch. So let's see about the numerical, that what has is given to you and what do we have to find. So consider the below diagram. This is shown over here, and the base resistance RB is given 50k. The 50 kilo ohm resistor is connected at the base, and the collector resistance is basically 0.7 kilo ohm. The collector resistance is given to us is basically 0.7 kilo ohm, and the VCC, that voltage supplied here, is 5 volt. And the beta value, you know that the transfer characteristic or the transfer equation for this transistor is basically beta, and this is given to you that 125. At the base input signal varying from 0 to 5 volt. This V in basically is varying from you can say that 0 to 5 volt. So if you vary this input, you see that there are two outputs that is varying between two states, that is 0 and 5 volts, as shown in the figure. So if you give 0 volt of input, you get a 5 volt output, and if you give the 5 volt input, you get 0 output. So these are basically working as a switch. If you give 0 voltage, the switch is basically, you see that the voltage is provided, the switch is off, and when you give this 5 volts, the switch is basically turned off. So let's see what has this asked us. So let's see the solution. So you have to find, the first thing that you always find about a transistor is basically the collector current, and you know that the collector current is basically nothing by using the Ohm's law, that is V is equal to IR. You can easily find the value of the current in the collector region. So the equation becomes I is equal to V by R, and the current is about the collector, so the voltage will be applied that is directly connected. You can see that the voltage connected to the collector is basically this VCC, and the resistor is basically RC. So the current will be this voltage divided by this resistance, and if you divide this voltage divided by this resistance, you get the value of current, and that is basically 7.1 milliampere. You find the value out of this equation, and this turns out to be 7.1 milliampere. The second thing you always find is basically the IB, and you know that the relationship between a beta and the currents is basically beta is equal to IC divided by IB. This was the equation that we already discussed in the previous lectures of regarding these transistors. So if you find the value of IB, you can just move this IB over here and beta in the denominator. So the IB becomes IC divided by beta, and you already found out the value of this IC, and this beta is already given to you. So if you divide this 7.1 milliampere that you just found out from here, the value of IC, and the beta was given to you, that is 125, you can get the value of the base current, that the base current will be 56.8 microampere. So from the above calculations, you can see that the maximum or the peak value of the collector current is 7.1 milliampere, while the VCE is equal to 0. So the VCE was 0, and basically this VCE, this is your VCE, from this collector to this emitter, this voltage is basically your VCE. So when the value was 7.1 milliampere, the voltage was equal to 0, and the correspondent base current to which the collector current flow in the 56.8 microampere. So it is clear that when the base current is increased beyond this 56.8 microampere, the transistor will come into saturation mode. It means that after you provide more than this current, that is 56.8 microampere, after this much current, the transistor will be turned on, because it will go into the saturation mode. So this was the first numerical, and you was asked to find the value of the current after which the transistor has to be switched on. So this is the current, and you just use two equations. The first equation was this to find the value of IC, and the second equation was this beta, this equation. So using just these two equations, you are able to find the value of this IB, and from there you concluded that after this much current, the transistor will be switched on permanently, because this is into the saturation mode. This has gone into the saturation mode, and you know that after the saturation mode, the transistor becomes switched on. This is your saturation mode from this side to this side, where that line becomes nearly straight. So consider the case when the 0 volt is applied at the input. Now let's have some further discussion. Let's say when you apply 0 volt as input, this causes base current equal to 0, as the emitter is grounded. So you know that if you apply 0 voltage at the base, the emitter and the emitter is grounded, there will be 0 base current, and emitter base junction is not forward biased, therefore the transistor is off, and the collector output voltage is equal to nearly 5 volt, accurately 5 volt, not nearly, it is equal to 5 volts. So when you basically apply Vi is equal to 0, and IB becomes equal to 0, and IC becomes equal to 0. So you see that this VC basically turns out to be the total collector voltage will be, you see that when you apply the voltage, you find the value of this VC, you have to apply KVL, and you know that this VC, basically the voltage at the collector, will be equal to the total voltage minus the voltage dropped across this resistor, across this RC resistor. So this voltage will be equal to this voltage minus this voltage. So the voltage turns out to be 5 volt, because you know that when this thing is equal to 0, this thing is equal to 0, this becomes also 0, and this becomes also 0. So when this becomes 0, this whole terms become 0. So when this terms becomes 0, the VC, or the output voltage, turns out to be 5 volts. Now consider the input voltage when applied 5 volts. So you just have to reverse this value. When VI becomes 5, so this IB becomes IB gets changed, and IB, the new value of IB becomes VI minus VBE, that is voltage from base to emitter, that is 0.7 volts, divided by this RB. So the new current will be this 86 microampere. So you see that at this region, and this current is basically greater than that 56.8 microampere. Let me just solve these equations for you. So from these equations, if you just put the value of this VI over here, you get 5 volt, and this VBE basically is, it's given that it's a silicon transistor by default, so you just have to minus or subtract this from this, and you have to divide the voltage by this RB, and RB has already given to you, that is this 50k. You can see that this is 50k. So if you divide this thing, so you get the value of the current at the base, and the base current turns out to be 86 microampere. So you now see that this 86 microampere is greater than it than the 56.8 that we already calculated in the previous slide, this slide. So this was the minimum current that was required to turn on the transistor and make it go into the saturation region. So after you apply this much of voltage at the input, you are actually providing the transistor the opportunity to go into the saturation mode, because this current that turns out is greater than the base actual current, that is 56.8. So this was the minimum current at which the saturation region starts, and now you are at much more current, you are giving much more current. So it means you are somewhere at somewhere like this, you are at this point, and this actually goes to straight. So this was the 56.8, and now you are giving it to the 86 microampere. So it is much more than the current needed to make the transistor go into the saturation mode. So therefore now you can conclude that if you apply if the base current is greater than this 56.8 microampere, the transistor will be driven into the saturation mode. It means it will be completely on or fully on, and for that you have to apply 5 volt of input at the input. Thus the output of collector becomes approximately equal to 0. So this was the case. You can see that this was the case. So if you apply 5 volt at this input point, this voltage turns out to be 0, and if you apply 0 volt at this point, this V out turns out to be 5 volt, resulting in 56.8 microampere. And if you apply 5 volt over here, this 56.8 becomes 80 microampere, and it is just 86 actually, 86 microampere. And this is the thing where the transistor has gone into the saturation mode. So let's take another example regarding this transistor as a switch, but this time let's take the PNP transistor. You know that PNP transistor is the working of this transistor is approximately same except the biasing. Except the biasing, they are working similar. The operations of both these transistors are approximately same. PNP transistor works the same as NPN for a switching operation, but the current flows from the base. So this type of switching is used for negative ground configurations. For PNP transistor, the base terminal is always negative bias with respect to the emitter. We have already discussed in the previous lecture number 4 actually. We have already discussed that how can you basically have to change the biasing when you go from PNP to NPN. You just have to change the biasing of the junctions provided in the configurations. You have to change the biasing from here to here. So in this kind of switching, the base current flows when the base input voltage is more negative. Simply a low voltage or more negative voltage makes the transistor short circuit. You see that in the previous scenario you have to increase the voltage from 0 to 5, but in this PNP case you have to actually uh, reverse the case. You have to apply the low voltage or more negative voltage to make the transistor go short circuit, or means switch on. Otherwise it will be open circuited and the input impedance will be very much high. So if the impedance becomes high, it means you are open circuit. And if the input impedance, the high impedance state becomes low, it means that you are providing the same scenario, that is more negative or low voltage, and these are causing the circuit to go in the short circuit mode. So as shown in the diagram, you can see that in this connection, the load is connected to the transistor switching output with the reference point. When the transistor is turned on, the current flows from the source through the transistor to the load and finally to the ground. So this is the path for the current. You can see that this is the path from the ground. So let's talk about examples of a switch, that where you can use the transistor as a switch. So the most common example that I provide to my students is to use the transistor as a switch specifically for LED, and this is a very good project if you want to create your own a lightning fountain. This is the thing that mostly people see in the New Year's evening, the lightning fountain. Let's talk about the Burj Khalifa. You see that there are different lightning patterns that create some kind of images, or you can use different kind of images to make a LED lightning fountain. So I'll also provide you an image in the after this slide. In the video you can see that what is lightning fountain, and this lightning fountain is basically nothing but it is a modified version of using the transistor as a switch to the LED. So you just have to switch on and off LED in a particular way so that it can form an image or a very good picture of anything. So you can use this transistor as a switch towards this LED. Using this LED you can have multiple options. You can have multiple colors actually. You can have green, blue, yellow, red, white, different kinds of lights sources, and using that different sources of colors you can actually create some kind of images, and this is as a whole is known as lightning fountain. And this is very much popular nowadays because of its impressions and their use. They are very much costly actually. This is not used by common man, but specifically for high or you can say VVIPs, functions or parties, etc. They use these kind of scenarios or this kind of system where they produce an image using these LEDs, and this is basically known as a lightning fountain. So how does this work? So when the switch at the base terminal is open, no current flows through the base, so the transistor is in the cutoff mode. We have already discussed that. Now I'm going to connect this modified version of this lightning fountain to the similar of operation of LED or the switch transistor as a switch that we just discussed and learned in the previous classes and in today's class as well. So if you apply the switch as a base, if you made the base switch the terminals base terminals open, there will be no current through the base, so the transistor will be in the cutoff mode. It means that it will be switched off. So you see that the LED becomes off. Instead of this load, let's say this is your load RC, instead of your load you put a LED over here. So the current, there will be no current and the circuit will be open, so it means LED will be off. When the switch is closed, base current actually starts flowing through the transistor and then drives into saturation, results LED become on. So if you apply some kind of base current, and that base current should be greater than some kind of value that we already derived in the previous example, you know that how you can find the value after which you can get the saturation region. So if you have reached that much of saturation point, you can make the LED become on. And the operation, or you can say the things that makes everything go very much easier, is basically the resistors. So resistors are placed to limit the currents through the base and the LED. So you know that if you vary this base resistor, you can actually change the value of the output as well. So if you increase very much, the impedance become high, so the circuit will go into turn off mode. If this resistance become low, this circuit will be turned on or switched off, switched on, or the it become short circuited. So these are some kind of parameters or resistors you can actually use to make your circuit go on and off simultaneously, or you can say to and fro. I will also discuss different more examples with you in the class as well, that how you can use this transistor as a switch in many multiple ways. There are so many applications of this transistor as a switch, and this is not confined or limited to just LED. You can actually put different motors, different routers, different machines over here, or different devices, different relays. You can actually turn that on and off, and using that further using that devices, you can actually create further modifications to make your own desires come true. So it is also possible to vary the intensity of LED by varying the resistance. You see that you can also change the, if you increase the RV value so much, if you increase this value to very high level, this becomes off. If you decrease the value of RV so much, this becomes on. And if you want to control the intensity of this light, like a dimmer, you know that what is dimmer? Dimmer is something that controls the intensity of a fan. That how can it similarly you can put a dimmer, but instead of a dimmer you can actually use a variable resistor. Variable resistor, sorry, this is not B, this is R. Variable resistor, variable resistor. And using this variable resistor, you can actually control the intensity of the LED. So you can see the diagram. This is the proper diagram, and this this will be the circuit that you will have to build by your own in your house. You can use this kind of these equipments if you want to make your own LED, your switch that is controlling your LED. So this is your LED. This is basically your light emitting diode. You just have to need these devices. The first one is 3904, or this 2 and 3904. Mostly the shopkeepers basically termed as is 3904 transistor. And you will also be needing a battery source about 9 volts. You can also use 5-volt battery source, but at that point you will be able to have this resistance very much low. But to keep it on a safe side, I recommend to go with the 9-volt, and this 9-volt is known as battery cell. Instead of this 5-volt charger, you can use a battery cell of 9-volt, 9-volt battery cell, or this is also known as gallon cell. Gallon cell, I'm not sure about the spelling. So this is the gallon cell. This is the shape of this gallon cell. This is this kind of cell is basically, one is round and other one is hexagonal. So this is the shape of this 9-volt gallon cell, and it cost about, let's say 40 to 50, but let's say 50 rupees to be very much on the safe side. You will be needing one LED, and this LED will cost you around 5 to 10 rupees depending on the color. Mostly the white colors is a bit expensive, so mostly it is somewhere between 7 or 8 rupees. But the normal LEDs, the red or the green ones, they are mostly around 3 to 4 rupees or maximum 5 rupees. You will also be needing a resistor that will cost you around 1 or 2 rupees. And the last thing that you will be needing is a switch as a button. So this will be costing you around 10 to 15 rupees as well. So on the safe side, let's say 20 rupees. This can be also a push button as well. but I already recommend to make it a permanent switch. So you can see that using these different tools, and you can build your own transistor as a switch to LED in just 100 to 150 rupees. You have the breadboard, which is the major thing. If you have the breadboard, you can make the circuit of this transistor as a switch to LED in just this much of price. So if you increase the types of LEDs, and if you increase the colors of the LEDs, or if you increase the number of LEDs, the prices will also go higher as you increase this devices or equipments that are required to make this circuit. So another example that is very much in use, I already told you that there are many more examples that should be discussed, and we will discuss that in class inshallah also. The major application for the using the transistor as a switch is basically when you want to drive the motor. So let's take a condition where you are using a, let's say, robot. This is your robot car, and you know that robot has four wheels. So let's say this is your first wheel, uh, and in parallel to that there is second wheel. Similarly, this is the front thing, and this is your uh, the back wheels. So let's say, and these are, let's say, connected to the axle. Let's say these are the axle. I'm not that much good in the drawing, so you have to bear it with me. So let's say you want your robot car to move forward, so you have to make the switch on, and the tires will move forward. If you want to go to reverse direction, so you will have to change the polarity of the voltage, so that the voltage will be negative and the motors will be rotating in the reverse path. So the remote will be going towards in the reverse direction. I will also provide you a video in the following slide, so that you can understand that how these things actually work. And if you want to the thing where this transistor acts comes into very much play is basically when you want to rotate your this motor. Let's say if you want to rotate this motor at left hand side, sorry, right hand side, so you have to stop this tire or this wheel, and you have to make rotations of this tire actually. So you want your this tires to be stopped, the tire at this side, and you want your this tire to move. So it means that you are switching off this tire and you are switching on this tire. So now there comes the play when you want to your transistor to drive your motor. And similarly, if you want to go left, let's say in this direction, so you have to make this tire stop now, and you have to make your this side, you this tire or wheel move forward. So as this tire move forward and this is stop, the remote or the car will move in this direction, because this tire is stopped and the other tire keep trying to move forward. So this thing will be follow this path, and this is very much in use. And the device or the IC that is basically used in certain applications or robots is basically L29 3D. This is the L29 3D. This is the driver IC actually, and you will be using this in the coming semesters for your if you are making some kind of mini projects. And such scenario occurs when you want to control a motor or a device or a robot car or any car. You will be needing this motor driver IC, and this driver is you can control using a transistor as a switch. You know that how you can make a wheel stop or on. If you want to make this wheel stop, you have to provide it zero voltage, so this wheel will be stopped, and you will have to apply plus voltage at this side, so this will move forward. So if you this will move forward and this is stop, this will be turned at this side. So this is also the example that we discussed in the previous class as well, so let's not repeat it again. But for those who haven't listened that lecture, I will also just give you a brief introduction. Using the transistor values, you are given the beta value 200 and the IC is 4 milliampere and the base current is 20 microampere. You have to find the resistor RB. You have to find the resistor from where for which the switch is completely on, the load is completely on, and the input voltage should not exceed 2.5 volt. It means that you are given with a circuit, and instead of this V in, you are asked to provide a certain voltage that should not exceed 2.5 volt, and beta instead of this 125 you are now given uh, 200 beta. Beta is equal to 200, and the other things are the same. So it has asked us to find the value of the base resistor, that what should be the value of this what should be the value of this base resistor, so that the device is fully on. So we have just used a simple formula of KVL, and using that KVL formula, let me show you. This is a simple formula for KVL. You have just applied the KVL formula over here, and from where you can find the value of this RB. RB is equal to V in divided by minus VB divided by IB, and V in is given to you, that is not should not exceed 2.5. So we have put the value of V in as 2.5, and VB is basically 0.7 by default, and IB is given to you, and that is 20 microampere. And if in the exam or anyone, if he doesn't give you this value, let's talk about this scenario as well. If anyone who hasn't give you this value, let me delete this. Let's say if you are not given this value, so the second alternate of this thing is basically you have to find this IB from this beta and this IC. You know that the relationship between beta and this current is equal to beta is equal to IC divided by IB. So if the examiner or anyone didn't give you the value of IB, you can easily find the value of IB by doing the same thing that we did in the previous example. You just have to calculate this IB using this IC, that is approximately 4 milliampere, and this beta, that is 200. So you will get the value of IB, and that IB should be you have to put that value of IB over here, and from that you can find the value of the base current that should be placed while designing a circuit, so that the switch is completely on and the voltage should not exceed 2.5 volt. So there are many more applications for which you can use transistor as a switch. You can switch different control lamps. I've already told you that you can use these switches to use or to control lamps, relays, or even motors. And I've also given you an example to control a motor using a motor driver IC. So this is basically a motor driver IC, and this is a DC motor driver IC, not stepper motor or servo motor. And you should note that this driver IC is not compatible with every mode of motor. It is only specified to the DC motor. For if you are using stepper motor or servo motor, there are different ICs for them as well. So transistors are fully turned on. This is a summary when you are in the saturation mode or saturation region, and they are fully off when you are in the cutoff region. While using a transistor as a switch, a small base current controls a huge or large collector current. So you know that if you increase a small kind of base current, the large current flows from the collector to emitter. So the collector current, load current will be greater. When you use transistors to switch inductive loads such as relays and solenoids, this is basically a flywheel. This becomes a flywheel diode, and we will be discussing this flywheel diode in the end of this lecture series, that because it is a topic that need to be addressed, but this is not the scope of this course. If you get the time, we will discuss that in class. And if you didn't, you will be discussing this diode in your machines or your other circuit analysis courses as well. So there is no need to worry. You will also learn this kind of diode as well in this course, in this in this program. uh, when a large current flows or voltages need to be controlled, and this is basically Darlington transistor. You can This is the most popular and most common for the beginners or immatures. You can say you can use Darlington transistor. You can find Google it by yourself. The mostly transistors that are used for beginners are mostly Darlington transistors. So that's all for today. I hope you have learned a lot. This By this lecture we have concluded our things regarding transistor as a switch. We have done approximately 2 to 3 numericals. We have discussed applications, examples, and different type of tools that you can use while using the transistor as a switch. So now you are in a good capacity and you are in a ability. Now you are able to build your own basic block diagrams or circuits. Actually, I will recommend and I will highly appreciate. I will also give a few bonus marks if you perform these experiments, like these experiments that I've just told you. You can see that I've already provided you a huge amount of information. Similarly, you will be using this kind of circuits in the coming semesters as well. So do not forget this information, because this is also necessary. I hope to see you in the class, and I will also look forward to your questions. I will highly enjoy, and I will highly appreciate if you ask any questions, any kind of questions, because you know that the more you ask, the more you learn. That's all for today. I'll see you in the class. Thank you. Allah Hafiz.